The journey of asteroid discovery represents one of the most fascinating chapters in astronomical history, evolving from simple visual observations to sophisticated technological detection systems. Beginning with Giuseppe Piazzi's landmark discovery of Ceres in 1801, our understanding of asteroids has transformed dramatically over more than 2 centuries. Originally considered mere minor planets, asteroids are now recognized as complex worlds, with unique characteristics that provide critical insights into the formation and evolution of our solar system. The history of their discovery involves pioneering astronomers, revolutionary mathematical techniques, and technological innovations that collectively expanded our cosmic awareness and challenged existing planetary theories. The first asteroid was discovered on January 1, 1801, by Italian astronomer Giuseppe Piazzi at Palermo, Italy. Initially mistaken for a comet, careful orbital calculations revealed that the object moved in a planet-like orbit between Mars and Jupiter. This location was significant because it aligned with the prediction made by Bode's law of planetary distances, which had hypothesized a missing planet in precisely that region. Piazzi observed the object until February 11th, when illness prevented further tracking. And despite reporting the discovery in the press, he shared complete details with only a few colleagues. This limited information exchange created a significant challenge: how to relocate the object when it reappeared in the night sky. This challenge prompted German mathematician Carl Friedrich Gauss to develop a groundbreaking method in 1801 for computing asteroid orbits from limited observations, a technique that remains fundamentally unchanged today. Using Gauss's calculations, German-Hungarian astronomer Franz von Zach rediscovered the object on December 7, 1801, with German astronomer Wilhelm Olbers independently finding it again on January 2, 1802. Piazzi named his discovery Ceres after the Roman goddess of agriculture and patron goddess of Sicily, establishing the tradition of discoverers naming asteroids, unlike comets which are named for their discoverers. The discovery of 3 more objects in similar orbits soon followed: Pallas 1802, Juno 1804, and Vesta 1807. These findings complicated the elegant solution to the missing planet problem and gave rise to a long-lived, though now rejected, theory that asteroids might be remnants of an exploded planet. The term asteroid, meaning star-like in Greek, was proposed by William Herschel in 1802, but wasn't widely accepted until the mid-19th century, when it became clear these objects were distinct from planets. After the initial discoveries, asteroid research entered a dormant period until 1830, when Carl L. Henke renewed the search. His persistence was rewarded in 1845 with the discovery of Astrea, the 5th asteroid, ending a 38-year gap since Vesta's identification. This discovery reinvigorated asteroid research, and by 1866, astronomers had cataloged 88 such objects, demonstrating remarkable progress after the long hiatus. The latter half of the 19th century brought significant theoretical advances alongside continued discoveries. In 1866, American astronomer Daniel Kirkwood identified gaps, now known as Kirkwood gaps, in the distribution of asteroid distances from the Sun, providing crucial insights into the gravitational influence of Jupiter on asteroid belt dynamics. The same year saw the discovery of asteroid 87 Sylvia, which would later become the first asteroid known to have more than one moon, though this characteristic wasn't confirmed until 2005. Similarly, 90 Antiope, discovered in October 1866, would eventually be recognized as a double asteroid with 2 nearly equal components, though its binary nature wasn't detected until advanced adaptive optics became available in 2000. The introduction of photography to asteroid searches in 1891 represented a revolutionary advancement in detection methods. Asteroid 323 Brucia became the first to be discovered through astrophotography rather than direct visual observation. This technological innovation dramatically accelerated discovery rates by creating permanent records of the night sky that could be meticulously examined for the subtle movement of asteroids against the fixed stellar background. By the end of the 19th century, the number of known asteroids had grown to 464, demonstrating the effectiveness of this new approach. The early decades of the 20th century saw theoretical frameworks for understanding asteroids develop alongside continued discoveries. In 1918, Japanese astronomer Hirayama Kiyotsugu identified clustering in 3 orbital elements among various asteroids. From this observation, he developed the concept of asteroid families, hypothesizing that these groups shared similar orbital characteristics because they formed from the fragmentation of larger parent asteroids through catastrophic collisions. This insight provided the first evidence for collisional processes in the asteroid belt and opened new avenues for understanding asteroid evolution. By mid-century, astronomers began developing more sophisticated theories about asteroid origins. Some proposed that Jupiter's gravitational influence had interrupted the formation of a planet from planetesimals located approximately 2.8 astronomical units from the Sun. This theory helped explain both the existence of the asteroid belt and its relatively low total mass, compared to what would be expected for a fully formed planet. Concurrent calculations revealed that asteroids passing close to major planets typically had lifespans of only a few 100,000 to a few million years before either colliding with a planet or being ejected from the solar system. This realization led to the understanding that asteroids observed in such orbits today must have entered them relatively recently, suggesting ongoing dynamical processes. The physical characterization of asteroids also advanced during this period, though observations remained limited by available technology. Astronomers began estimating asteroid sizes based on their brightness and assumed albedo, though these estimates often contained significant uncertainty. Despite these limitations, the catalog of known asteroids continued to grow, with each new discovery adding to the understanding of the asteroid population's diversity and distribution. The latter half of the 20th century witnessed unprecedented acceleration in asteroid discovery and characterization. While earlier research focused primarily on cataloging asteroids based on their orbits, modern astronomy began investigating their physical properties in detail. New observational technologies enabled scientists to determine asteroids' size, shape, rotation period, composition, mass, and density, transforming them from mere points of light into complex geological bodies worthy of dedicated study. Several landmark discoveries expanded our understanding of asteroid complexity. In 1994, images from the Galileo spacecraft revealed that asteroid 243 Ida possessed a small moon, later named Dactyl, the first confirmed satellite of an asteroid. This discovery fundamentally changed perceptions of asteroids, demonstrating that they could host their own mini-systems. Asteroid 433 Eros became particularly significant as the first near-Earth asteroid discovered, the first to be detected by radar, and eventually the first to be both orbited and landed upon by spacecraft. These direct encounters provided unprecedented data about asteroid composition and structure. The rate of asteroid discovery increased exponentially toward the century's end. From 4 in 64 known asteroids at the beginning of the 20th century, the number had grown to 108,066 by its conclusion, and exceeded 1 million by the third decade of the 21st century. This remarkable acceleration resulted primarily from automated sky surveys designed to identify near-Earth asteroids that might pose collision threats to our planet. These programs employed sophisticated computer algorithms to analyze digital images, identifying moving objects automatically, and calculating their orbits with previously unattainable precision and efficiency. Modern research has revealed extraordinary diversity among asteroids in terms of size, shape, composition, and orbital characteristics. The largest asteroid, Ceres, with a diameter of approximately 939 kilometers, has been reclassified as a dwarf planet, while thousands of much smaller bodies populate the main belt. Some asteroids display unusual configurations, such as 216 Cleopatra, with its distinctive ham-bone shape and 2 satellites, or 288 Glauca with its exceptionally slow rotation period of about 1,200 hours. Compositional studies have identified several distinct asteroid types based on spectroscopic data, with the most common being C-type, S-type, and M-type. These classifications provide insights into the material properties and potential origin of different asteroid groups, with some likely representing primitive material largely unchanged since the solar system's formation, while others show evidence of significant thermal processing or differentiation. Particularly intriguing are asteroids like 16 Psyche, a predominantly metallic world approximately 223 kilometers in diameter that may represent the exposed core of a protoplanet, whose outer layers were stripped away through violent collisions. The discovery of asteroid families has provided valuable information about collisional processes in the asteroid belt throughout solar system history. By identifying groups of asteroids sharing similar orbital elements and compositional characteristics, astronomers can reconstruct catastrophic breakup events and better understand the physical properties of the parent bodies. This reconstruction offers a window into the dynamic evolution of the asteroid belt and the violent processes that have shaped it over billions of years. The history of asteroid discovery represents a remarkable scientific journey spanning more than 2 centuries, from Giuseppe Piazzi's serendipitous observation of Ceres in 1801 to today's sophisticated automated surveys identifying thousands of new objects annually. This progression has been marked by key theoretical and technological innovations, from Carl Friedrich Gauss's mathematical techniques for orbit determination to the introduction of photography and digital imaging, that have each accelerated the pace and precision of asteroid discovery. The evolution of asteroid science reflects broader patterns in astronomical research, transitioning from simple cataloging efforts to comprehensive physical characterization and direct exploration. Each advance in our understanding has revealed asteroids to be more complex and scientifically significant than previously recognized, offering crucial insights into solar system formation, planetary evolution, and potentially even the origins of life's building blocks on Earth. As technology continues to advance, particularly in automated detection systems and spacecraft capabilities, our knowledge of asteroids will undoubtedly expand further, continuing the remarkable journey that began with a single unexpected observation on the first day of the 19th century.